Hey, thanks for joining me. This is Chapter 3, Section 2.1, Polynomial Functions. It's really an introduction to polynomial functions. And so the first thing I want to talk about is just this notation that looks like this. F of x equals a, we read this as a sub n times x to the n power plus a sub n minus 1 times x to the n minus 1 power plus, and then we get dot dot dot, a sub 2 to x squared times x squared, and then a sub 1 times x plus a sub 0. Okay, now what on earth does this mean? N is going to be the term number, but it's actually the number of terms plus minus 1, right? Because the first term is going to be, or the last term is going to be a sub 0. So that's called the constant term. And then there's a whole bunch of other terms, and they all have x in them, and x to various powers. So let me give you an example, the one that you know very well, the linear function. And it goes like this, y, or f of x, equals, and let's just go ahead and make it general, mx plus b. Right? And b would be the a sub 0, that's the y-intercept, the constant. And then here we have x to the first power. Okay, so that's this one right here, x to the first power. And then here we have the coefficient of x to the first power. That is a sub 1, whatever that number is. So that we normally think of that as the slope. But that is, this falls into the category of a polynomial function. Let me give you a second one. F of x equals, let's say, 3x squared plus 5x minus 7. Okay. What is that? Well, that's a quadratic. We just talked about quadratics. And look at here, it has a constant term at the end. That's the y-intercept again. That's our a sub 0. And then 5x, well, there's x to the first power. And then we have the coefficient of x to the first power, which we'll call a sub 1. That's the coefficient of the x to the first power term. And then we have an x squared. And then we have a number that's being multiplied by x squared, which is 3 in this case, so that's going to be our a sub 2. And it's possible that that number isn't there, like it could have been just x squared plus 5x minus 7. So what would a sub 2 be in that case? Well, it would be, a sub 2 would in that case be 1, because if there's no number there, you've got x, or x squared in this case, with no number, then the number is 1. So a sub 2 is 1. Let me give you one more. Let's write, we'll do g of x this time. Let's say g of x is equal to x to the 4th power plus 3x squared minus 5x plus 1. Okay, so let's label each of these pieces. This is a sub 0. That's the constant term. X to the first power is there, and then we have a sub 1, which is negative 5, then x squared is there, and then we have a sub 2, which is positive 3, and then x to the 3rd power. Oh, there is no x to the 3rd power. Well, it actually exists. It's right here. It's in between x to the 4th and x to the x squared, but you can't see it. Why can't you see it? Because a sub 3 is equal to the number being multiplied by x to the 3rd power, but x to the 3rd power isn't there. It's gone. It's nothing. Therefore, a sub 3 must be 0. Okay, and that's going to come in handy. That's going to be really important later on. Okay, so then we have x to the 4th power, that's there, and a sub 4 is 1, because there's no number there, so the coefficient of x to the 4th power is 1 in this case. The coefficient of x to the 3rd power is 0 in this case. Now let's look at the pattern. The pattern says that we always start with our polynomial functions are always going to start with a power of x and a coefficient of x, and we label them with the same number. So in this case, the power of x is the fourth power, and the coefficient in this nomenclature is called a sub 4, and it's just a fancy way of saying the coefficient, or the number that is the coefficient of x to the fourth power. And then the formulation, this general form says that every a sub n x to the n power term in a polynomial function is followed by a sub n minus 1 x to the n minus 1 term, meaning that if there's an x to the fourth power term, there has to be an x to the third power term. And is there here? Well, sort of. There wasn't an x to the third power term because, well, we say there is an x to the third power term, but the coefficient was a sub 3 was 0. So there's always a slot for x to the, if there's an x to the fourth, there has to be a slot for x to the third power, even if the coefficient is 0. And then there has to be a slot for the next number down, x squared. And this dot, dot, dot is just saying, there could be lots of them. We could have started with x to the 15th power, and then there would have to be a slot for x to the 14th and the 13th and the 12th, all the way down to x squared, which we have here, and x to the first power, and then x to the 0 power. Well, we don't write that because x to the 0 power is 1, so it's just down to the term without an x at all, which is the constant term, the last term. So that's what this general polynomial function notation means. It just means that we can expand this idea. We've been slowly expanding the polynomial functions. We had x to the first power, right, a linear function, then we did a quadratic, x squared, and now we're going to expand a little bit faster. We're going to say, well, could we have x to the third power, x to the fourth power, x to the fifth power, and what we're saying here is, we don't need to do them all one at a time. We can just say that we can describe them in mass as this general polynomial function. Okay. And then we're going to talk about, and this is a giant topic in algebra. You've done this before. This is a giant topic in algebra, and we're going to talk about how to deal with these and how to describe them. And the first description that we're going to use is just what are the end behaviors, the end behaviors. So I'm going to erase all this, and I'm going to talk about the end behaviors of a polynomial function, the graph of a polynomial function. And so let's see, let's write that down, the end behaviors. And the end behaviors are going to be based on that first coefficient, okay, a sub n, that coefficient, and the first power of x. Okay, and there's going to be 4 options. Okay, there's 4 options. We could do a little grid here, but I'm not going to. Instead, I'm going to scroll down just a tiny bit here and give you 4 coordinate planes. So the idea is if you have a function where the first coefficient is an odd number. So we have an odd coefficient. A sub n is an odd number. And x, I'm so sorry, let me start over again. Okay, let's say it again. A sub n is positive. I knew I was saying that wrong. If a sub n is positive, and then n is odd. N is odd. A sub n is positive, n is odd. Then what that will look like is the graph is going to go down to the left and up to the right. Now let me show you this. If it looks like this, y equals 3x plus 7. Right? This is a positive number. The exponent is odd, and the graph is going to look like this. Right? It's a pretty steep slope. It's going up to up to the right, down to the left. That's a linear function. But if I had y equals 2x to the third power plus 4, okay, the graph might look like this. It would go up, and then it would come down for a little bit, and then it would go back up again. It hit the y-axis at 4, and it would go up to the right and down to the left. And if it was, and I don't want to belabor this, but if it was, some positive number, 1/3 x to the 5th power, odd again, and we can have lots of other x's, right? Plus 3x squared minus 7x plus 5. Then the graph, I don't know exactly what it would look like, but I know it would go down to the left like that, and then it would go up, and then it would come down, and then it would go up, and then it would come down. And let's see, 1, 2, 3, 4, and then it would go up again, and eventually it would go up to the left, up to the right and down to the left. Okay. So a polynomial function, they all have these same characteristics. Like in the middle, they're going to do weird things in the middle, right? And this linear function is just going to be straight. Cubic function, it's going to go up and down a little bit. Maybe there's some bending or curving there. If it's the 5th power, it might go up and down, up and down, up and down. If it's the 7th power, it would, it could potentially go up, down, up, down, up, down, up, down, a bunch of times. But whatever happens in the middle, we know that the left side is going to go down and the right side is going to go up. And that's going to be the pattern that we're going to see. Now, let's get rid of all that and see if we can describe what happens if the first term is negative. So here we go. We're going to change our color here, and let's say that a sub n is a negative number, and the power, the exponent, is still odd. Well, what does that do? It just changes the directions. And we know this is true because we've dealt with linear functions. If the number next to x to the first power is negative, that means the slope is negative. It's going down. It's going downhill. It goes up to the left, down to the right. And it turns out that all the other functions do the same thing. Okay, now let's think about what if that a sub n was still positive and the exponent was even. We actually know one of these. F of x equals, let's say, 2x squared plus x minus 5. Okay, what does that look like? Well, we know what it looks like. The graph looks like this. It's a parabola. It's going up to the left and up to the right. So the two ends, to the left and to the right, are going to go both up. They're going to increase without bound. Now, if it was, let's say, g of x equals x to the 4th power plus 3x squared minus 7x plus 1, whatever, then that would go up to the left, and then it might come down, and it might go up again, then it might come down some more, and then it might go up again, but it's going to go up to the left and up to the right. So that's the pattern that we're going to look for. And then finally, if the first term was negative, right, that ax squared plus bx plus c, if the a value is negative and the highest power is even, then both the ends are going to go down. And again, we've seen this on a parabola. If that first term is negative, that just means that the parabola is opening downward instead of upward. And the same is true for any even-powered function. So h of x is x to the 6th power plus 3x to the 5th power minus 5x to the 4th power plus 2x to the 3rd power, right? And you just keep on going. The graph, I don't know what the graph is going to look like in the middle, but if it's negative in front, it's going to go down to the left, down to the right, and it might go up and then down and then up and then down and then up and then down. In the middle is going to go, it might start to go up and then curve and then go back up again. So all sorts of curves can happen in the middle, but the end behavior is going to look like this. Okay, now let me just real quickly point out something in this pattern, and that is this, that if this is true, if we know this, then we also know something about the what we call the zeros. Okay, if the power of x, the highest power of x is 3x, like let's see, we'll do this. Let's see. Well, let's start like this. X squared. If the I'm sorry, getting myself mixed up. Let me start over again. X to the first power. If the power of is x to the first power, that's the highest power of x, then we know it's a linear function, and we know that when we graph that it's going to have one point where it hits the y-axis, the y-intercept. It's going to have one point where it hits the x-axis, the x-intercept. Okay, we didn't really worry too much about the x-intercepts when we were doing these. We mostly worried about the y-intercept. Okay, but when we got over to x squared, a function with x squared, remember that in that case we knew that there was a parabola, and there was this potential that the graph was going to go down and then come back up again, and it was going to hit the x-axis twice. Now, there's still one y-intercept, and we cared about that a little bit. That was helpful. But the big thing we cared about was those x-intercepts. Those x-intercepts. And we called them, we actually had a name for them, we called them the roots. Okay, that's where the graph of the function hits the x-axis. And remember that back when we were talking about quadratics, there is this possibility where the quadratic kind of parabola comes down and goes back up, and it never touches the x-intercepts. There's no the x-axis. There's no x-intercepts. There's no roots, and that could happen in either direction, right? Could have been shaped like this, opening downward parabola, but never goes as high as the x-axis. Okay, so that two roots, that number of roots, is a potential, right? For x to the first power, it's not a potential. It has to have one x-intercept. But for x squared, there can only be, like, we're not guaranteed to have two x-intercepts. It's just that's the most we can have. Okay, well, let's continue the pattern. X to the third power. We know that x to the third power is going to go down to the left. It's going to go up to the right. And then the potential there with x to the third power is it might have like a turn downward, and then it turns back up again. Okay, that's a potential. Now, it might not do that. It might just go up and then take a little jog and then keep on going up like that. So it's possible that it doesn't have this full-on turn the corner and go back down and then turn back up again. But it's a potential, and therefore there is this potential that we have 3 x-intercept hits the x-axis 3 times. Okay. Now again, it doesn't have to, but we can say it does have to hit the x-intercept. It has to hit the x-axis. Having it one x-intercept has to hit it once because it's going down to the left, up to the right. So it has to be one intercept, but it doesn't necessarily have to have all 3. Okay. Let's look at x to the fourth power, and once we're done with this one, we can stop. X to the fourth power, we know that one goes up to the left, up to the right, unless it's a negative coefficient, which means down to the left, down to the right, but we'll just do this one. With x to the fourth, it could be the case that it goes down, and then it turns the corner, comes back up, and then it turns the corner, goes back down again, and then it turns the corner and goes back up again. So now think about this. This could have how many x-intercepts? Well, it's possible that it has 4 x-intercepts. Right? Still only one y-intercept. Y hit the y-axis only one time. That's characteristic of all functions. But it could hit the x-axis 4 total times. So we can say that 4 is the total number of x-intercepts possible. It could be less than that. Now imagine if I took that x-axis and I dropped it down. Maybe the graph looked more like this. Let's take away the x-axis there and make a new one. So it's possible that there's only two intercepts. Yeah, because this one time it goes down and then turns the corner and goes back up again without getting to the x-axis, but the second time it goes down, it hits the x-axis and then turns the corner and goes back up again. So it's possible that there's only two. So it could be that there's four, could be that there's two, but it could be, and let's draw one more x-axis, it could be x-axis down here. And so this graph is completely above the x-axis, it never touches at all. So it's possible that there is 2 or 4 or 0 intercepts. So now notice the pattern here. If the power of x is odd, then there has to be one intercept for sure, one. But it could be two more than that if up to the number of the power. So the number of intercepts is either 1 or there has to be 1, right? But if it's 3, it could be 1 or it could be 3. 1 or 3. And if it's 5, x to the 5th power, the number of intercepts is going to be either 1 or 3 or 5. For even powers, it's either the number, right, 2 intercepts, or it's 0. 2 or 0. And if it's bigger than 2, like 4, x to the 4th power, then the number of intercepts would be 4 or 2 or 0. And if it was x to the 6th power, then the number of intercepts would be 6 or 4 or 2 or 0. Those are the potentials. Because what goes up must come down, right? So what goes down must come up. In an even power, you go down, and then you go up, and then you go down, and then you go up, and you go down, and you go up, but you have to end up going the same direction at the end that you went at the beginning. But with an odd, you go up and then down, then up and down, and then up. You have to go in the opposite direction. So you always have that one spot where you're going to definitely for sure hit the x-axis, but all the others are just potentials. Okay, that's the big idea with polynomial functions. Two things: the end behaviors, number one, and number two, the middle behaviors. We don't know for sure what they're going to do until we graph them. We can use technology, but we do know that they are going to have those characteristics. Okay, so once we know that, then we can start talking about finding the zeros of a polynomial. We can say, what are the zeros here? And a big part of the rest of the chapter is going to be tricks and tips for finding the zeros. So for this first one, I'm going to use the factoring method. So if I want to find the zeros of a polynomial, the first thing I look for is, can I factor the polynomial? And in this case, I can. This one's fairly easy to factor because there's a common factor of x. So I can cancel. I can factor out the x. So x cubed plus 4x squared plus 4x is equal to x times x squared plus 4x plus 4. And then that trinomial, x squared plus 4x plus 4, that one's pretty easy to factor also, I think. Let's see if we can do this. That is x plus 2 times x plus 2. And so I have three factors, x plus 2, and x plus 2. Now notice that if any one of those factors is equal to 0, if any one of these is equal to 0, then the whole thing is equal to 0, because in a product, when you multiply a bunch of things together, if one of those things is 0, the whole thing is 0. So the zeros, the whole thing is going to equal 0 if x equals 0. That's the first one. Or if x equals negative 2, because negative 2 plus 2 is 0. Or if x equals negative 2, oops, that's a second x equals negative 2. So we are going to call that a double root. In other words, one of the places where the graph crosses the x-axis is at x equals 0, and y is going to equal 0 there. And another place is at x equals negative 2. But notice that in this function, the first term, the coefficient, is positive. The power is odd. That means it's going to go down to the left, up to the right, and because it's cubed, it potentially is going to go up, turn the corner, go down, and then turn the corner and go back up again. But according to our finding the zeros, there's only 2 zeros. How do you get 2 zeros where you go up, hit the x-axis, come back down, then go back up again, and hit the x-axis again? It hit the x-axis at -2. We're going to say it hit it twice because it went up, hit -2, and then it turned the corner, went back down, and it was still on -2 as it was going down. So that's a little bit weird, but we think about that. If there's a double root, it means there's a spot where the curve of the graph actually just kissed the x-axis and turned around immediately, went back down again without crossing it. Okay, so that's what that one did, and then it goes back up again and it hit the x-axis again once more, going through the x-axis and going on up to, because the right side has to go up forever, the left side has to go down forever in this type of polynomial. Okay, that's what's going on here, and we actually went a little bit further than we were supposed to here, because we were supposed to just find the zeros, which were 0 and -2, and number 2, -2 was a double root. Okay, so one of our roots is 0, and then one of them is -2, but -2 actually occurs twice. Okay, so that's what's going on with that one. Now let's graph this. And again, instead of getting out our t-chart and just starting to plot points, x, g of x, and y, x, y, instead of getting our t-chart out, we're going to rewrite this, and we're going to try and see if we can evaluate this using some kind of our knowledge of algebra. So the first thing I'm going to do is I'm going to put it in standard form. So it's g of x equals -x⁴ minus x squared plus 6. So my first coefficient here, the coefficient is negative. It's -1. And the power, the first power, highest power, is even. So I know that the graph is going to go down to the left. It's going to go down to the right. And there's a potential of hitting the x-axis 1, 2, 3, 4 times. I don't know if that's going to happen, but there's my potentials. Okay, now I'm going to think about factoring this, and we did factoring before with something weird like this. Remember what we'd said? We said, well, let's make x squared equal to n, and let's make x⁴ power equal to n squared, right? So n and n squared, x squared is x⁴ power. So we can change this to negative n squared minus n plus 6. Okay, and then let's factor out a -1. So I'm going to just take out -1, and then what's left is n squared plus n minus 6. And then when I factor n squared plus n minus 6, I get n plus 3 n minus 2. And there's a -1 factor there as well. Okay, now because we're looking for zeros, that -1 doesn't really matter because the -1 doesn't really matter because -1 times the 0 is still 0. So we can factor out that -1, we're okay. Then let's let's see what our intercepts are, right? Because if n plus 3 is a factor, then n equals -3. And if n minus 2 is a factor, then n equals 2. Okay, so those are our zeros for the n, but remember that n stands for x squared. So really we have x squared equals -3 and x squared equals 2. So we have to continue solving using the square root. So we're going to do the square root of both sides. And so x equals plus or minus the square root of -3. Well, that's undefined. So there's going to be 2 roots that don't exist, right? Remember, x⁴ power means there could be 4 roots, 4 spots that we hit the x-axis, but we don't have to hit it 4 times. It's possible we only hit it 2 times. Okay, so then x squared equals 2 means x equals plus or minus the square root of 2. Well, what's the square root of 2? The square root of 2 is 1.3, 1.4, something like that. So I have, and let me erase my graph here a little bit. So now I know that there are 2 roots here at -1 point something and +1 point something, but there's 2 roots that don't exist. So my graph is going to go up across the x-axis, and then it's going to come back down, but it's not going to hit the x-axis again because I don't have 4 roots, I only have 2, and it's going to go up, and then it's going to come back down again. I know that there's going to be some symmetry here because all of the powers are even. So the x to the fourth, x to the second, x to the 0 power, all the powers are even. So I know there's going to be some symmetry there. And then I also know that that constant term is the y-intercept, and that's actually 6. So I've misdrawn my graph here. Let me see if I can sketch it again. I'll do a better job. So I know it's going to go up. It's going to hit the square root of 2, or the negative square root of 2, and then it's going to go down, but it's going to hit it's going to hit 6, it's going to go up, and then it's going to go down again and hit positive square root of 2. Okay, my drawing isn't so good, but you can see kind of what this looks like. Now, fun activity to do, go to desmos.com. You want to click on the graphing calculator, desmos.com, or you get your own graphing calculator out and type this in and see what it looks like. You got to zoom back, and you can see that it's going to look kind of like this. It's going to be a pretty skinny graph. It's going to go up. Not going to have a whole big turnaround here. I suspect it's not going to turn around too much there. It's going to come back down and go through the positive 1 point whatever that is, 1.3 I think. Okay, so there is how you're going to graph. We're not like just plotting points at random. We're thinking about what are the end behaviors going to do, what are the y-intercept, where it hits the y-axis, and what are the x-intercepts, and by the roots, what are the roots, the x-intercepts, and then we're going to sketch it in from there. Okay. Let's do one more. I think this is the last one. And here I'm going to show that we can plot some points also. So we'll do it all together here. So first of all, h of x equals x to the fourth minus 6x cubed plus 9x squared. So that's kind of in standard form. Highest power is x to the fourth power. The coefficient is of x to the fourth is positive, so we have positive coefficient. Fourth power, we know the end behaviors are going to be up to the left, up to the right. We know it's going to come down, go back up, down, go back up. Potentially there's going to be 4 roots. Let's see if we can figure out what they are. Okay, we're going to use factoring. At this point, all we know is factoring. We're going to learn other methods as we go through the chapter. Let's see. Factor this. First of all, I see there's a common factor of x squared. So let's get that out of there. X squared times the quantity x squared minus 6x plus 9. Okay. Now, x squared is a double root, right? If x equals 0, then x squared is 0, and the whole thing is 0. But there's 2 x's there. There's x and x. So there's actually 2 zeros. So 0 is a double root. So x equals 0 is a root, and we would say that's a double root, right? Because there's 2 x's that are factors. And then the, let's see, x minus 3 times x minus 3. I think this is a perfect square, and it is. So then x minus 3 times x minus 3, so x equals 3 and x equals 3. Wouldn't you know it, we have another double root. So x equals 0, and that's a double root. X equals 3, that's a double root. So what does that mean? Well, let me erase my markings here. So we know now that the graph is going to come down. It's going to hit 0, and it's going to hit 3. And when it hits 3, it's going to turn around and go back the way it came. And when it hits 0, it's going to turn around and go back the way it came. So it can't be going from the bottom and hitting one of those spots and then turning back around. That can't be the case, because in that case, the ends would be going down to the left and the right. So it has to be the case that it comes from above, hits 0, and then immediately turns around and goes back up again, and then it turns around again, goes back down, hits 3, and then immediately turns around and goes back up again. Okay, so now we know that that's kind of what the graph is going to look like, but that's good, but there's still a lot of unanswered questions here. Notice that there's no constant term, right? Plus some number, plus well, the constant is 0, plus 0, so the y-intercept is 0, so that's not really helping us very much. Let's think about how can we find some more information about like what's going on between 0 and 3, and what's, maybe how quickly are the graphs going up to the left and to the right. How can we find that out? Well, we can get our old trusty standby, the t-chart, out, and we can say, okay, well, now that I know kind of some of the key points here, I know that there is a point 0, 0, and I know that there is a point 3, 0. Let's find the other points maybe between those. So how about let's try 1, and we can plug 1 in. So I'm going to do h of 1, and that equals 1 to the 4th power minus 6 times 1 to the 3rd power plus 9 times 1 squared. That's pretty easy to do, right? 1 to the 4th power is 1, so 1 minus 6. Oops, I can't draw there. Plus 9, and so that is 4. So 1, 4. I can plot that point. We'll do that in a minute. Let's do 2. So we'll try this h of 2, and we'll get 2 to the 4th power minus 6 times 2 cubed plus 9 times 2 squared. Okay, so that's 2 times 2 is 4, 4 times 4 is 16, so 16, and 6 times 8 is 48, so that's 4 minus 48, and then plus 9 times, let's see, 2 times 2 is 4, and then just 4 is 36, so that's 52 minus 48 is 4. Oh, wow, look at that, 2, 4, 1, 4, 2, 4, and then 3, 0, and 0, 0. So let's plot those points now that we've got a little bit more information here. We can plot these points, and we can say 1, 4, 2, 4. And then if we really wanted to know, we could plug in, and I would use my calculator for this. I can plug in, like I want to know what happens at 1.5. So I can do 1.5 to the 4th power minus 6 times 1.5 cubed plus 9 times 1.5 squared. Definitely that's a calculator problem. I'm not even going to bother to do that here. I think we've gone on long enough. I think we'll see that the graph looks pretty similar to this, and that's going to give us a fairly accurate graph. I encourage you to do it on your technology, on your graphing calculator, on the Desmos.com, just to check it out and see. But there it is. Thank you very much for watching.